In this example, we will explain the calculation of osmotic pressure. We will look at a cross-section of a very simplified system that could be used to measure osmotic pressure. So the important point in this diagram is that there's a semi-permeable membrane between two liquids. So this membrane will be permeable to the solvent. So only solvent can move through the membrane. On the left side, the green is the solvent, the liquid. On the right side, the green is a solvent and some solute, something dissolved in solvent. So it's a mixture. And you'll notice that the way this is drawn, there's a height difference between the left side and the right side. And this height difference is due to the fact that there is solute in the solvent, and it corresponds to a pressure difference. So delta P is the density, G, and then the height. From understanding of phase equilibrium, at equilibrium, the fugacity on the left side for the solvent equals the fugacity on the right side for the solvent. And we use the notation where the hat indicates that we have solution. So I can write the fugacity of the solvent on the left side. Since it's pure solvent, I don't need the notation in case solution. And this is the solvent measured. So remember, left side, right side, measured at the pressure on the left side. That's going to be equal to the fugacity on the right side. Since it's not pure, you have the mole fraction of the solvent, the activity coefficient, and the fugacity of the pure solvent. But remember, this is at a different pressure. This is at the pressure on the right side. Call this equation 1. So first I'll correct for the pressure differences between the left side and the right side. And so the fugacity of the pure solvent at the pressure on the right side would be the fugacity of the pure solvent to pressure on the left side, and then the Poynting correction for how fugacity of a liquid changes with pressure. It's a small correction. So pressure on the right side minus pressure on the left side divided by gas constant and the temperature. And this V is the volume of the liquid. Left side or right side, it's going to be the same, but it's, so maybe I should instead just say the volume of the liquid solvent, molar volume. And this pressure, the right side minus pressure on the left side, this is what is called the osmotic pressure and is normally represented by pi. So what I've done is just combine equations 1, 2, and 3 and relate the fugacity to solve on the left side to fugacity to solve on the right side. So notice this cancels with this, and so we've simplified the equation. We can further simplify it and say that the fugacity coefficient for the solvent is essentially 1. And the reason we can say this is because the mole fraction of the solvent is large. So the mole fraction of the solvent is close to 1. This simplification is good when we have 98% solvent, a couple percent, 1%, etc. of a solute. We can make that substitution, and then we can solve for the mole fraction of the solvent as this exponential of now minus that osmotic pressure, the volume of the solvent liquid, and that's a molar volume, the gas constant, temperature, and that's, of course, absolute temperature. And we're going to simplify this equation just by taking the log of both sides, because it'll turn out to make it easier to work with, and then we can solve for the osmotic pressure. So we can rearrange this, and so we have the osmotic pressure in terms of the gas constant, absolute temperature, the volume of the liquid solvent, and the log of the mole fraction of the solvent. Now remember that the mole fraction of the solvent is close to 1. That allowed us to make the approximation here about the activity coefficient. It also allows us to use an approximation from math that the log of the mole fraction of the solvent when it's close to 1 is equal to the mole fraction solvent minus 1. And we can substitute that in here so that we have the osmotic pressure, again in terms of liquid volume, gas constant, temperature, and 1 minus the mole fraction of the solvent. Of course, 1 minus the mole fraction of the solvent is the mole fraction of the solute. So we end up with the final equation, and we'll just rearrange it slightly. Liquid equals mole fraction of the solute now, RT. So this equation looks a lot like the ideal gas law. It's a pressure, osmotic pressure, right? Osmotic pressure, the molar volume of a solvent, absolute temperature, gas constant, and then this is the mole fraction of the solute that we've dissolved in the solvent to cause this pressure difference. And so the osmotic pressure follows directly from the relation between the fugacity being equal on both sides of the equation.